There's one final chapter left in this unit, which is called Theory Unification. This is optional, and the goal of this chapter is certainly not to make you an expert on any of the new theories of matter and the universe and energy, but just to present some terms to you so you can understand the richness and the beauty of physics research as it is going on today. So let's look at the status. This chapter started by discussing how physicists at the end of the 19th century were somewhat comfortable with what they had explained. Electricity and magnetism had been unified through the work of Faraday and Maxwell and many others, and mechanics and thermodynamics were pretty well understood. Then quantum physics hit, and the rest of the 20th century was spent explaining the physics of very tiny particles and objects that move very fast, and of course more information on light. And now, with dark energy and dark matter, it turns out that all of our physics has been only looking at roughly 4 to 5% of the universe. That's a pretty low number. There's much more to discover. So this unit will summarize some of the key developments after quantum physics started in the first decade of the 20th century. Quantum electrodynamics. That provides an integrated explanation of relativity, quantum mechanics, and electrodynamics. Those are pretty difficult topics on their own, and quantum electrodynamics, or QED for short, integrates all of them. It describes how light and matter interact and has made phenomenally accurate predictions that have been verified by experiment. It was started by Paul Dirac and Hans Bethe, and then Sin Itiro Tominaga, Julian Schwinger, and Richard Feynman were awarded the Nobel Prize for completing the work. Feynman summarizes this terribly complex theory with 3 pretty simple points. Photons, light, move from one place in time and space to another. Electrons move from one place in time and space to another. And electrons emit or absorb protons. That's it. These 3 things right here. Now, of course, there's just unbelievable work done to further explain what this is, but this is kind of Feynman's summary. Drawings of these interactions, which are called Feynman diagrams, enable very complex calculations to be made and then experiments carried out to show that they actually work. The Electroweak Interaction. This integrated the descriptions of electromagnetism and the weak force, the weak nuclear force, that is responsible for the radioactive decay of nuclei. These forces are very different at low energy, the energy we're used to dealing with, but at energies greater than 100 GeV, they are one force, and that force is called the electroweak force. Abdus Salam, Sheldon Glashow, and Steven Weinberg were awarded the Nobel Prize for their work in this area. And again, as we go over the next few slides, this is the key word, integrate. Everybody's looking to see if we can integrate all these various forces in the universe with one explanation. Quantum chromodynamics. For the longest time, the proton and the neutron were considered fundamental particles. That's found not to be true. Each one has an underlying structure, and each nucleon is actually made up of 3 quarks. This is the field of quantum chromodynamics, which explains the strong nuclear force and how it interacts. Quarks are attracted to each other, and they're attracted by exchanging gluons, which is yet another particle. And the further quarks get from each other, the more strongly they are attracted, unlike gravity and electromagnetism, but very analogous to a spring force. And the range of quantum chromodynamics, the range of these forces, is basically the size of a nucleus. So as the quarks get further away, the force is stronger, but it only acts over a very tiny distance. Now, the people who worked on this were Gell-Mann, Nishijima, Wigner, and Zweig, and they were key contributors to this field. The Standard Model. There are 4 basic forces known: the electromagnetic force, the weak force, the strong nuclear force, and gravity. The Standard Model integrates 3 of these. It explains the electromagnetic, the weak nuclear, and the strong nuclear force, and it has 61 elementary particles. Particles that have no underlying structure. That's the definition of an elementary particle. Such as quarks, photons, electrons, neutrinos, muons, W bosons, etc. Note that protons and neutrons are not considered elementary particles as they are made up of quarks. Many of these particles can only be seen by colliding other particles, such as protons, with each other at extremely high energies and then measuring what comes out. People have made the analogy to trying to understand how a car works by taking two cars, accelerating them towards each other at 70 miles an hour, crashing them, and seeing, again, what comes out of it, and then trying to rebuild the car. This makes the experiments, not the car, but the particle experiments, very complex and expensive. The Large Hadron Collider that was built on the border of France and Switzerland cost approximately $5 billion and has already found the Higgs boson, which explains how mass exists in the universe. Nature is making it harder for physicists to more completely explain the atomic world. Recall, the Millikan oil drop experiment was done on a lab desktop. Now we're using tremendously high energy and high expense colliders to further look at what's going on in the universe. What about the gravitational force? Well, we're now talking about the grand unified theory. It comes out of the Standard Model, but it is still not completely explained. It seeks to add the gravitational force to the three other forces, that is, the weak nuclear, the strong nuclear, and the electromagnetic force that are covered by the Standard Model. To date, there is no satisfactory grand unified theory. Gravity is such a small force compared to the other three. It's an order of 10 to the 25th smaller than the weak force, so it's hard to integrate with the same theory. Also, gravity still has not been integrated with quantum physics. String theory. Many physicists are unhappy with the Standard Model as it has so many elementary particles and it does not include all four fundamental forces. String theory is an attempt to fix these problems, and it states that all particles are made up of tiny vibrating strings, and the way they vibrate gives rise to different properties such as mass and charge, which are evidenced to us as different particles. It is very theoretical. It is mathematically beautiful. It unifies all four forces. However, it requires the use of multiple dimensions, anywhere from 10, 11, 12, as opposed to the three physical dimensions and the one dimension of time, and many different parameters to explain the universe. It also allows for the possibility of multiple universes. However, it has not made any predictions that can be tested yet because the energies to test this are way beyond the capability of humans. So many physicists consider it more of a philosophy than physics, and there's a debate going on right now about string theory and of course all the other theories to explain what's going on with the universe. It is fitting that we end this chapter to talk about something that we can't see, don't know what it is, but we think it's there, and it comprises a large part of the universe. This is dark energy and dark matter. The universe has been expanding ever since the Big Bang. However, it is not only expanding, its expansion is accelerating, which should not be happening if gravity was the only force affecting the expansion. The expansion should be slowing down, since gravity is an attractive force, or at the most just staying the same. To explain this phenomena, physicists have proposed the existence of something called dark matter and dark energy, which comprise, by calculations, 95 to 96% of the universe, but cannot be observed, and this is accelerating the expansion of the universe. So just when we think we can explain nearly everything, or at least get close to it, here comes something that 95% of the universe is made of, and we cannot see it or know what's going on with it yet. So there is plenty more research to do.